distinct pleasure today to have a guest speaker, Michael Greisinger, who's a forecaster with the National Weather Service and National Oceanographic and Atmospheric Administration based in Chanhassen, Minnesota. Michael brings to us information today with respect to climate and in particular the effects of changes that may be occurring in the climate and how they might impact airport operations and aviation. So without further ado, I'll have Mike come up.
No, I guess that comes actually working today. So I was doing the taps actually for Minneapolis today. But glad to be out here. I'm always glad to get out of the office when I can. I'm also happy to report that as far as I know, there are still no complaints of noise in the city of Carver, where I live. But an action-packed 20 minutes nonetheless is what we have. By quick, I mean really quick science refresher. I'll just breeze through, maybe, there we go. Just some of the climate change evidence, trends, and causes for that. Some changes we've seen in Minnesota, then kind of a what to expect, and then any aviation impacts, and trying to, could we see any impacts on how operations are run and at MSP. First of all, I just wanted to point out, I think we've all heard the term greenhouse effect. This is the extent of your science refresher. Basically, the Earth's atmosphere kind of acts like a greenhouse. The sun's energy comes in, heats the ground, ground heats the air, but the air is going to absorb some of that energy and send it back to the Earth, and that's what kind of warms us. The biggest thing I just want to point out there is it's natural. There's nothing man-made about the greenhouse effect. In fact, most estimates put its effects of warming at about 60 degrees Fahrenheit. So if we didn't have the atmosphere, we'd be on average across the entire globe 60 degrees colder, which means we wouldn't be here right now. So the greenhouse effect is natural, and we need it to survive. Where climate change comes in is by increasing greenhouse gases, we're increasing the impact of the greenhouse effect. So that's really where global warming is coming from when they're talking about increased gases. It's just increasing the power of the greenhouse effect. If you think global warming, I think the first image for a lot of people that comes to mind is something like this chart. You know, the temperatures going up, especially after 1980, really accelerating. I just want to point out, though, it's not just temperature. So that's what all these charts are. By the way, this all came from the latest IPCC climate assessment, which they released last year. So there's where all these charts come from. Anyways, there's your land air temperature increasing. The surface temperature of the oceans is increasing. The air above the oceans temperature is increasing. Sea level is gradually rising. Summer Arctic ice coverage is decreasing. And in fact, the acceleration of these summer sea ice loss in the Arctic has been quite stark here in the last 10 years. The temperature within the troposphere, so just the depth of the troposphere is about 20 to 30,000 feet deep. Just that entire depth in general is increasing in temperature. The upper 700 meters of the ocean is increasing in temperature. Our atmospheric moisture is increasing. So we have a more moist atmosphere. Slight decrease in northern hemispheric snow cover in the spring, and then the glacial mass, those mountain glaciers and things like that, they're all decreasing. So just the thing to point out there is it's not just temperature. There's a whole bunch of other indicators that are showing we have warming going on, and certainly our atmosphere, our climate is changing. This map just shows the temperature increase from 1901 to 2012. Everybody pretty much across the globe has seen warming, but where it's most stark is up in the polar regions. It's where radiation processes dominate. So where nights are long and radiational cooling takes over, that's where the warming has been the greatest. And so that's why the warming has been the greatest toward the poles and gradually decreases as you head toward the equator, unless you're in the Sahara Desert, at which point there's not much moisture there, so yeah, the water vapor isn't as big of an impact. Precipitation trend-wise, probably harder to see, but the big thing to point out there is we are seeing an increase in precipitation, but it's weird. We're seeing an increase in precipitation, but a decrease in the number of days with precipitation. So when we get it, which means you end up with a lot more potential for floods, but then at the same time, droughts. A kind of wild world. Why all the changes? Well, there are natural causes for change. Everything from continental drift, of course that takes millions of years, Slight changes in the Earth's tilt, there's slight changes in the Earth's orbit. You have decadal or shorter oscillations, things like the Pacific Decadal Oscillation, El Nino and La Nina and things like that. Changes in solar output and volcanic eruptions as well, all impact or kind of natural impacts on climate. But the big thing to note with a lot of those is look how many years it takes for that to really impact the planet. It's long periods of time. Anthropogenic or human causes, which is the fancy scientific word for that, is anthropogenic. It's just a result in increased greenhouse gases, the biggest of which is carbon dioxide. This in turn increases strength of the greenhouse effect, but not all anthropogenic sources result in warming. There are things like increased particulates that will actually reflect the sun's energy and lead to cooling. But when you add all the warming and the cooling together, you get a net warming. And really the only way to explain the warming trend we have seen is through anthropogenic forcing. And the fun thing about models is if you want to know, well, how would things be different if we didn't have an increase in CO2? Well, you can take the amount of CO2 we had in 1850 measured from glacial cores, and you can hold that number constant and run your model. And that's what the climate scientists did. That red line there is the models are kind of on the bottom, and what do you notice they do? They just kind of follows things along pretty good to about 1980, and then things go a different direction. So at least the models, which are based in physics, it doesn't explain the warming we've seen. When you add in just anthropogenic forcing, you don't have natural forcing. It picks up on the increase in temperature, but it gets a little too crazy with that increase in temperature with just anthropogenic forcing alone. And when you add the two together, at least with the models, you're able to recreate what has happened in the past with our temperatures. So that's why we say the big overlying force in there is anthropogenic forcing, but the natural forcing is in there as well. So quickly moving along, what have we seen in Minnesota? There's just our temperature trend. You can see it's been gradually increasing, but if you split it out by season, you'll notice our greatest increase, winter. In particular, winter minimums. It does not get as cold at night as it used to, period. Last year was an exception. But that's where our biggest warming has been, in particular, nighttime lows. But also it's bled into the spring, but all seasons have seen warming, but it's especially the winter into the spring where the warming has been most noticeable. I was going to talk more about trends in lows of -10 or less, but I just put this up here now for more of an FYI. You ever wonder where the Twin Cities climate record comes from? Well, from 1938 to present, it is MSP, the big airport. From that point back to 1894, it was downtown Minneapolis at the Weather Bureau. And then from, I think it's 1894 or 91, I can't remember, it was with the St. Paul Signal Service in downtown St. Paul, which goes back to, I think, 1878. So we sliced those three records together to take the Twin Cities climate record back to 1878. And now you know. Precipitation-wise, we've seen same thing increase there. You see a big dip there with those brown numbers. Anybody want to take a guess at what decade that was? The 1930s. So that's that big drought in the 30s. But you can see a lot of wet years. But if you break it out by season, what do you notice? Is our biggest increase has actually been in the fall. Why the fall? Well, we're getting summer rains now in September, and Novembers are warmer. So we're getting more rain as opposed to snow in November as well. So we're kind of getting both ends is giving us more precipitation in the falls. In general, more precipitation. So we'll move into the future. This is mid-century, essentially, the kind of the 20s into the 30s, 2020s, 2030s. On the left is just expected temperature increase, and the right is the variability within the models. The big thing to note is the temperature increase is most noted on the top left, which is winter months. That's where we're continuing to expect to see the greatest increase in temperature, and an increase in the summer, but not quite as much as what you're seeing in the winter. And then also the highest variability is with temps in the winter. So wild winters, I guess, is the thing I take from that. Look at just recently, 2011, 2012 was the third warmest winter of all time, followed up 2 years later, and by last winter, with the 9th coldest of all time. And what about precipitation, kind of DJF, which is winter, more precipitation in the winter. More, same thing when it goes into the spring, March, April, May. And then when you get to the summer and the fall, it's kind of either drier or a little change with precipitation pattern. The kind of trend we're seeing is wetter winters, especially wetter springs, and then things kind of drying out in the summers and falls. And that's certainly what we've seen the last few years. What can we expect in Minnesota? First of all, increased variability with the weather, more extremes. Dry, wet, hot, cold, and just a lot more extremes. That's the thing you hear from climatologists. More extreme weather is what you can expect. With winter, it's winter. Daylight is still only 7.5 hours or something like that in the winter, so we can't escape that part of physics. So it's still going to be cold. It's still going to be winter. It's still going to snow. But when you add, there'll be a lot of variability, but when you add things up over time, you'll just see what we've continued to, or have seen, you'll continue to see it, which is just gradually ticking up with temperatures. Springs, highly variable. Some will be cold, some will be warm, but just about all look to be wet. And that's just very active. Springs are what we've seen. Summer heat, more summer heat waves is the big thing with the summer. And in addition, fewer precipitation days, but more or similar precipitation. So heavier precip when we get it. And then falls, milder also with less snow because fall is considered, November is considered fall, even though it's technically really a winter month up here. All right, so the last little part, how about aviation impacts? Probably the biggest impact to aviation will be thunderstorms. And if you work in the FAA and you try to fly planes, direct planes around the country, the controllers will probably tell you their worst thing are thunderstorms because they're big and you can't fly through them. And we're going to see an increase in thunderstorm days. A warmer atmosphere, more moisture, more instability means more thunderstorms. Snowstorms, as they say, they impact a terminal, but thunderstorms impact jet routes as well, not just the terminal. An example I like to give, if you're going from Boston to San Francisco with a blizzard over Chicago as opposed to a line of thunderstorms. Blizzard over Chicago, you fly over, wave, and nothing really changes. There's not much impact to your route. There's a thunderstorm, all of a sudden you're going up through northern Michigan and northern Minnesota. You're deviating, that's going to cost, you're flying more, you're going to burn more fuel, it's going to cost more money. Potential delays depending on how busy the routes are you're trying to get. Most likely they'll send you up through Canada. They love their can routes in the summer, as they like to call them. And as a result, I like to say in the winter, your flight's likely to be canceled. They say big snowstorm coming from Minneapolis. What the heck does Delta do the day before? There goes 40% of their flights the day before. They'll cancel ahead of time rather than have people waiting for 3 hours on the tarmac. In the summer, you don't see that happen. So you end up typically seeing a lot more delays in the summer, and cancellations are fun in the winter. This chart just shows increase of days with severe weather. With severe weather by the end of the century. And notice east of the Rockies, we're seeing increased. This is just severe weather. Well, if you're seeing more potential days of severe weather, you're going to potentially have more thunderstorms. So that's the big thing. Just more days with thunderstorms, more headaches for the folks at the FAA. How does weather impact or determine airport operations? The height of the clouds and the visibility, that tells them how many, can I take 90 aircraft this hour or can I only do 30? That's what that determines. And wind direction tells me, am I going to take the 30s or the 12s, or what direction is the airport going to operate on? So I asked the question to the state climatologist, probably hard to read, has there been a change in prevailing wind directions at Minneapolis? And Greg Spoden's our state climatologist, if you didn't know. And I loved his quote, so it's verbatim here. He said, I can't imagine a scenario where the general circulation pattern will be so disrupted that the prevailing seasonal wind directions will change. If that happens, we'll be facing far bigger problems than airport noise abatement. So in other words, you're not going to maybe see a noticeable change, but there is one change with the winds that we're seeing. And it's more subtle, but we saw it, actually, I think the chair there pointed it out in December. So it was kind of a nice segue into this. There is a subtle change. There's weather patterns, an increased tendency to become, the jet stream to become blocked, weather patterns to become stuck. There's examples like December, you end up with a whole lot. What are you doing with all these southerly operations in December? We should just be hammering away on the north winds, but we weren't this past December. Last winter, we didn't have a lot of southerly operations because we were in north winds. Again, we had a big block out to our west, and we were stuck in northwest flow. It's happened the other direction as well. So think of the spring of 2012, where it was summer by March. But it happens. What's a block? If you've ever looked at an upper air pattern, there's a block off the west coast. That's what last winter looked like. Big block off the west coast. Think of putting a stream, a big rock in the stream. What's the water going to do? It's going to flow around it, right? The same thing happens in the atmosphere. And it's going to go around that block, and you end up with these big dips and troughs and big ridges and kind of an amplified weather pattern that at the same time tends to be stagnant for days or even to months at a time. So that's what kind of goes on there. And that's just big thing there is you end up with prolonged periods where winds come out of a direction where you're maybe not expecting it to for that time of year. Why the blocking? Biggest thing's the loss of Arctic sea ice. This leads to a weaker temperature gradient between the cold poles because they're not as cold and the warmer mid-latitudes. Temperature gradient is what drives the jet stream. That's why it's there. But if the temperature gradient isn't as strong, your jet stream isn't going to be as strong. And a weaker jet is more conducive to developing those blocks. And this is just a picture of where the Arctic sea ice was and kind of where it's expected to be by the end of this century, which is just hugging the northern coast of Greenland. So it's an expected trend to continue. This is just a windrows. I don't know if you've ever seen this, but the bigger the bar is, the more you see a wind out of that direction, just to quickly sum it up. So there's the average wind that you see at MSP. And what do you notice about, if you look at the airport, the way it's laid out on the left, what do you notice? Boy, those runways, those parallels pretty much line up with the prevailing wind direction. That's the reason why you're in these meetings with a bunch of people around South Minneapolis and not the Highland neighborhood of St. Paul. Because just the prevailing wind direction just means, that's where we're going to send the aircraft. How does blocking impact that? We'll go to July of last summer. So there's a typical July windrows. What do you notice dominates? Southerly winds. If you wonder what it looks like in January, flip it around. It looks the same, except the more winds are on the northwest as opposed to southeast. Well, what happened in January of 14? Well, we had a whole lot of northwest wind. I don't know if you remember that. So we would have had a whole lot. You'd have seen a lot more operations on the 30s this past July. And there was a big impact with that on temperatures as well. We hit 90 twice. That was it on our hottest month of the year. We even had 2 days where, one day with highs in the 60s this past July. That was a block that set up similar to last winter where we're cold, northwest flow. You can't go the other direction. There's a typical March. It's 50-50. It's a transitional month. That's why March typically we'll see a 50-50 operation because, like I say, we're transitioning from spring, more northerly to more southerly winds. But March of 2012, what do you notice is missing in that chart? It's northerly winds. So March of 2012, we would have been operating like we do in July as opposed, or August. And that happens. And of course, there was a big impact there. We had 9 days that month with highs in the 60s. The average high in March goes from, 30 at the start to 41 at the end. So 9 days in the 60s, 7 in the 70s, 1 in the 80s. An odd mark. But that was where a block helped us, in that case, be warm. And it stayed in on the whole month. So I'm done. There's somebody's humor about a heat wave. Well done. We're rare up here, but I'll take some questions if there's time for questions. Hopefully I didn't drag on too long.
Well, thank you, Michael. That was wonderful. I just have one observation that I'm wondering if you can verify when you talk about the increase we're seeing in severe weather and in thunderstorms. I mean, not simply related to us, but intercontinental. Is that one of the reasons we see these increases in nighttime operations because we have planes flying around bad weather that aren't getting in here on time, they're getting in late and therefore departing late? Has that been more of an issue than, let's say, 15 years ago?
More than anything, what makes that an issue is we probably have more operations than we did 15 years ago, I would assume. But, depending on the timing, the key is this timing of when those thunderstorms happen. You get a middle of the afternoon, your kind of peak traffic time, and you get a big line of thunderstorms that stretches from New Orleans to St. Louis, and you got to get traffic all around that. A lot of times, it's not just that, but what terminals get impacted? Is Atlanta getting impacted? O'Hare, the New York terminals? Because if you get delays there, that's going to stack up the system everywhere else, and all of a sudden a flight that was supposed to get in here at 8 or 9 is getting in here at 10, 11, midnight, and you get people in Egan are saying, why are you turning around at this time of night here? Or, folks in South Minneapolis are just like trying to sleep with the windows open and got planes roaring overhead all night. But yeah, I mean, that'll make the impact. It's where they happen is what really matters.
Right.
So, especially if those thunderstorms hit at Dallas, Chicago, Atlanta, a busy airport, it can really get delays going, and then you'll see your uptick, especially in the summer of night operation.
Are there any other questions, observations? Yes.
Thank you, Chair. Given the variability increase in a lot of things here, can you predict whether or not storms are going to become less predictable in terms of direction and how far out you can predict where they're going to go and their nature?
With the storms, actually, with our modeling and power is increasing quite a bit. So from the forecast perspective, at least days in advance, we should get better at that, being able to, hopefully, especially for thunderstorms, be able to plan better 24, 48 hours in advance, just with the models being better and being better at showing where the thunderstorms are. But from the seasonal perspective, I think it's still going to be tough to, December, for the winter, are we going to have a whole lot of southerly winds and a really warm winter and a lot of operations on a different runway than we're used to and type of things? That's going to be harder to predict, but within 48 hours, I actually think it'll be easier to, we'll start being better at predicting at least weather within 48 hours, timing it in and things like that.
Thank you.
I have another question. Could you address volcanic ash, not necessarily in terms of global warming, but in terms of the immediate weather effects from having ash in the air? And my understanding is we've had a fair amount of ash over the last few years.
Yeah, the ash, and if you go back and you look at a temperature record, you can see when the big, like Pinatubos and things like that blew, because you'll see the temperature trend just for 3 years, bang, down, because it takes about that long, because those big mountains, when they get, to really have a volcanic issues impact the weather, you need to get this stuff into the stratosphere, because if the ash gets into the stratosphere, it's not going to get mixed out as well as it will down in the low levels. But the recent volcanic activity, I don't know if it's had too much of an impact with temperatures. More of an issue with that is we've seen a big the Pacific Decadal Oscillation. Actually, about 2010 or so, actually flipped signs. It went from a warm phase, which it was in since about 1980, and flipped into a cold phase, which I think has had a bigger impact for why we've been able to be cooler here, because those cooler temperatures out in the northern Pacific Ocean warmer temperatures. Oh gosh, we get all confused. Anyways, but that switch in the PDO that we've seen since about 2010 has actually increased the amount of ridges we've seen in the Pacific Ocean. And the ridge out in the eastern Pacific, you go downstream, by the time you get here where we're in northwest flow. And so that's kind of cooled things down a little bit. But when that flips the other way, and it'll be off to the races again for us. So.
Chair.
Yes, Mr. Hart.
Michael, certainly appreciated your presentation. I found it very worthwhile. Curious question, where are we at in the sunspot cycle that you mentioned?
Oh, the sunspot. Yeah, I don't know where we are. I mean, the sunspot cycle, I'm trying to remember. I think we just got finished a maximum, if I can remember correctly, in 2010. A max. And we're heading back down. But what was weird is it was a max, but we have satellite records going back, records of sunspot activity and solar output going back at least into the 50s or so. And even though we had a max sunspot cycle, it was the weakest max we have observed before, which is interesting. But we're trending back down into a low. It's about a 10-year cycle, so we're about halfway through that.
So it's a 10-year cycle high to high, so for 5 years we would be on a downward
trend. It's
about,
I think it's like high to low.
Oh, high to
low.
So
yeah, you usually get your low. Our low was about 20,000. We hit another high at about 2010, and by 2020 we'll be back down into the trough and then running back up.
And so that would be predictably cooler temperatures for the whole Earth based on that cycle?
Yeah, the sun's, I'm trying to think. Actually, I think the sun is cooler actually with fewer or cooler with more sunspots, if I remember correctly.
Oh, the opposite, counterintuitive.
Yeah, but it's a minimal change when you look at just the percentage-wise, the output we're seeing, the watts per meter squared we're seeing at the top of the atmosphere, the max sunspot to min sunspot cycles, minimum percentage. So it's there, but it's not a huge influence. So it's not like you're seeing the sun's output drop by 30% every 10 years or whatever.
Thank you. Thank you very much.
Are there any other questions? Yes.
One more. Thank you, Chair. I haven't watched this closely, but it seems to me that when we first started hearing about El Niños, whatever number of years ago, it was like a surprise, and their prediction seemed better than it is now. What's going on with the science of that phenomenon?
The prediction's done well there. That's the one thing when it comes to predicting winter temperatures. The one thing where we have confidence if it's going to be warm or cold is El Nino, because we actually can predict it. We've been able to do that. We've done a good job because there's a lot of data arrays out there, so we've collected a lot of high-density ocean data, not just at the surface, but at depth. And our climate models seasonal climate models have actually done pretty good at being able to predict those. They were showing us going El Nino, and we just kind of sputtered out this winter. We're still kind of a, I guess, neutral phase, a warm neutral phase close to El Nino. But yeah, as I say, the predictability there is, I'd say, is increased there, and that's just, our understanding with that's just the highest. I mean, the biggest thing there. Now that our models they're coupled, as they say, it's not just an atmospheric model. There's an ocean model as well, and they talk to each other. And now that we've been able to do that, we've actually kind of been able, because it's such a large-scale phenomenon, we've been able to predict it. Thunderstorms are, tiny. Those are hard to predict in a model because chaos happens when you have equations you can't solve and you have to kind of estimate. But those larger-scale features like the ENSO, we're actually kind of be able to predict on a seasonal basis. And that should continue as we move forward.
Anything else?
I guess I have one more question.
Okay. No, that's why Michael's here.
Last year, all of us, I think, in this room added a term to our lexicon called the polar vortex.
Oh, yeah.
Right? I'd never heard of it before after being in the aviation industry for quite a while. Obviously, it's not a new thing. Why do you think that was such a big deal last year? I know it's the core of the coldest air, but what causes the polar vortex to drift over us, and what do you see about the future of Minnesota and polar vortexes?
Yeah, the polar vortex, basically, it's the core of the Arctic air. Right. And it's just a deep, cold, low-pressure center. It's always there. It's always been there. The reason it got so popular last year was probably because of a thing called Twitter. And someone started throwing the term around, and it just caught fire from there. It's a fun term to say why it's been so cold. One of the things is some more research needs to be done on that, but some early findings from research. It might be another one of those impacts of the loss of Arctic sea ice. We're getting more cross-polar flow, if that makes sense. Flow coming from the Bering Sea over to Siberia, and what that does is it shoves the polar vortex one way or the other. If it's last winter, it kind of pushed it down to Hudson Bay, and it brought the cold air to North America. You go to the 11-12 winter, the same sort of thing happened, except it got shoved over into Siberia. That winter, incidentally, we were one of our warmest here. That was a very cold and snowy winter in Europe. So then it just got pushed to the other side of the hemisphere in that case. But that's one of those things where it seems counterintuitive with we're getting warmer, but we could see an increase in cold winters here as we continue to lose sea ice because we're changing wind patterns across the Arctic, and we're forcing that cold dome of air to kind of move farther or closer to the pole or equator than you'll usually find it. But yeah, I mean, it's always there. It just because of somebody caught on to it last year, kind of went viral. So now everybody knows of it. And now meteorologists, when they hear that term, usually roll their eyes.
All right, thank you very much.
Yep.
Thank you. Is there anything else? Well, I would just like to say thank you again.
Yep.
I feel like we've spent such good quality time with you. We're calling you Michael instead of Mr. Greisinger, but we really enjoyed the presentation, and we hope you'd be open to coming back sometime if we have additional questions or concerns.
Oh yeah, anytime. So I'll hang out for the meeting. So
Great.
if somebody has questions afterward, you can come bug me.
Great. Thank you very much.
Yep.